In this lesson, we're going to be looking at the inverses of relations, and in particular, we're interested in the inverses of relations that actually give us a function as an inverse. So first of all, just the general rule, and all of this that we're going to be talking about in this lesson is review from past courses. When we talk about the inverse, the simplest conceptual way to do that is to just swap all elements of the domain and range. And you swap those directly if you have points. So in my first example here, I have a point AB, so the x coordinate is A and the y coordinate is B, and I have another point CD. So the way I find the inverse to that relation is I simply take my first point, I swap the x and y coordinates. I take my second point, I swap the x and y coordinates. So that's the first way. If you have points, you can go from any relation to an inverse relation. It has nothing to do with it being a function right now. We're just talking about relations. Now, in order to do it using an equation, generally we're going to be starting with functions in this case. Rarely are you going to be given a relation, just a generic relation that's not a function. And one of the reasons for that has to do with, in most cases, you're probably going to be starting with a function because you're going to be starting with something that's already in the form y equals something. And when you make this swap, when you switch from y equals, you're going to swap the x and y variables and then rearrange it back into the form y equals. When you make that step, it's very possible that this inverse that you've created might not be a function. So usually you'll be starting with a function in this case. You can see from the graph we have here, actually there's an example. That is the radical function. This one is y equals the square root of x. And then in order to find the inverse of this, we swap our x and y. You know what, I'm just going to go ahead and do that. We have an example coming up later where I'll do that, but since I've mentioned it here, so we start with y equals square root of x. We're going to perform this swap of x and y, so we end up with x equals the square root of y. In order to get y isolated, I square both sides, so I end up with x squared equals y. And so you can see that is the equation of, if I write that in the more traditional sense, y equals x squared, that is the equation of a parabola. Now in this case, it's only 1/2 of the parabola, and that's going to get into questions about domain and range, which I'm going to discuss shortly. Visually, if you take a look, here I have the original, in this case, function, the radical function, and I have its inverse, and these are mirror images of each other. We've talked about reflections. We talk about horizontal and vertical reflections, which occur in the x-axis and the y-axis. We can also take reflections in any line, and in this case, a reflection in the line y equals x, which is this dotted line, that's how you can visually represent an inverse to a relation. So you can see that these red and blue lines are mirror images across this dotted line. Now this is all stuff that you've covered before, but you may not remember it, so you need to do some work, do some study, and bring that back. Now expanding upon that idea of reflecting, and also borrowing from that the idea of making use of the points that I was discussing before. So here is, in blue, I have the graph of the parabola y equals x plus 5 all squared minus 2. So the vertex of this is going to be at -5, -2, which is marked here. This parabola opens up. There's no vertical scaling, no vertical reflection, so the step pattern applies. Over 1 up 1, over 1 up 3, over 1 up 5. To the left, over 1 up 1, over 1 up 3, over 1 up 5. In order to find the inverse of this, we can take any points. You can see I focused on 3 different points here, but it's arbitrary. The vertex is a good idea in this case because it's a parabola. So I take this point which has the coordinates -5, -2. I reverse those coordinates and I get -2, -5. So I plot that new point. I take the point -3, 2, which becomes the point 2, -3. negative 2, 7 becomes the point 7, negative 2. And if I did this for more and more points, I would end up describing this inverse relation, which is a parabola tilted over on its side. And you can see I've put in the line y equals x. That's our mirror line. That's our line of reflection. And as you can see across that line, this point to this point, there's a right angle here, and this is an equal distance. And that's what it means to take a reflection. Same thing is true here. We have a right angle, and I'll use a single dash because these two distances are not the same, and a right angle here, and these two distances are the same. Different than some of the others, but they are the same as each other. So that's how we achieve a reflection. Easier in this case, rather than worrying about the actual reflective part, that's a good visual way to check things, but really what I've done here with the coordinates and swapping the x and y coordinates is a far more reliable and much simpler way of achieving this. And I also note here that the inverse is an inverse relation. It is not an inverse function because it fails the vertical line test. Okay, now we have mapping diagrams, something you're not going to see a lot of, but I do like to mention. First of all, textbooks love mapping diagrams. Generally, you're probably going to list things in terms of a set of points, a set of x, y, and a table of values, or maybe you're going to write a set of points in a domain or a range. But for some reason, textbooks like to use mapping diagrams, and also we just want to expand our mathematical knowledge. We don't want to be unfamiliar with valid representations. So here we have what's known as a mapping diagram. And what this essentially does is it relates x coordinates and y coordinates to each other, assuming x is my independent and y is my dependent variable here. So this is saying that when x is equal to 0, that maps onto y value of 1, which is essentially saying that the point 0, 1 is in the relation. 0 is part of your domain, 1 is part of your range. If your mapping diagram only ever has a single arrow from the domain to any element in the range, then you know that you have a function. So, and another way of thinking of that is saying, when x is equal to 0, how many values of y can I have? Because remember, graphically we need to be able to pass the vertical line test. So when x is equal to 0, so we've got something right here on the x-axis. Here I've got 0, 1. So there's the point 0, 1. Well, if I had another value that corresponded to x equals 0, that would be 2 points stacked one on top of each other. And of course, that fails the vertical line test. So having a single arrow from each element, that's a function. When we take the inverse, all we're going to do is reverse the direction of the arrows. And then, to know whether or not the inverse is a function, now we can only have one arrow going from right to left. Here we could only have one arrow going from left to right. Now, I think it's easier to see this with a counterexample where we have, and it's important here, I'm going to start off with a relation that is a function. And some people are going to get tied up by this, which is we've got 4 points to 3 and 8 points to 3. Well, that means that there's a point 4, 3. When the x-coordinate is 4, there's a y value of 3. When the x-coordinate is 8, there's a y value of 3. Well, is there anything wrong with that in the terms of a vertical line test? When the x-coordinate is 4, the y-coordinate is 3. So that would be a point there. When the x-coordinate is 8, then the y-coordinate is also 3. Is there any problem with those 2 points being at the same height? No, of course not. That's perfectly fine. If you think about something like a parabola, parabola has lots of points that are at the same height. But the important part is that they are at different x values. Now this is not a parabola. This is just 3 points. And the third point, I might as well put it on here, that's 7, negative 3. That would be around here. So this passes the vertical line test. If, however, I take the inverse by reversing the direction of these arrows, then in this case, you can see that I would have one of my points would be negative 3, 7. Another point would be 3, 4. And yet another point would be 3, 8. And now we run into the problem that I was discussing before with the vertical line test. 1, 2, 3, negative 1, negative 2, negative 3. Negative 3, positive 7, let's say that's up here. Positive 3, 4 would be around here. And positive 3, 8 would be up here. And you can see there's going to be a failure of the vertical line test through these 2 points. And that's why we end up with the inverse in this case is not a function. Even though the original relation is a function, the inverse relation is not a function. This is subtle, something you're probably going to have to grapple with a little bit, and if you need to do these extra little steps, it's great if you can remember the rule, or if this you obviously want to get to the point where this makes enough sense to you. You don't have to remember things in terms of rules, you just understand domain and range and how to turn that into an understanding of function or relation. But if you need to do these intermediate ideas, list out your points, do a quick little sketch. These are all tools, and there's a reason why we teach them to you. So you can use these tools to help improve your understanding and come up with the right answers. Okay, now a lot of what we do is algebraic notation. We learn about graphical notations and different ways to represent things, but we're often most interested in an algebraic notation because when you are writing things by hand, that is by far the most convenient way to do this work. So the first thing we need to remind ourselves of is notation. So if we start off with a function, first of all, this means our starting relation has to be a function. So that's our first condition. That only occurs then. If we take the inverse and it turns out the inverse is also a function, we use this special notation. So I just want to remind you, again, this is something you should have that should have been exposed to you before, or you should have been exposed to before, which is that normally a negative 1 there represents an exponent. So a variable to the negative 1 or a constant to the negative 1 is 1 over. It is the reciprocal of that value. But this very special notation, function notation, when you see that f to the negative 1 or g to the negative 1 of x, that means I'm talking about the inverse of a function. I'm not talking about a reciprocal. And then the other thing, and this is probably something that's been said to you before, and this is one of those ones where it just comes with understanding, the idea that a function and its inverse undo each other. And this is a very important concept in mathematics. And what it's saying, and it comes back to the idea that a function is like a machine. A function takes some input that goes into the function, and then you get the output on the other side. The way that an inverse works is it says take the output you had before. So you know what, rather than saying x and y, I'm going to be a little bit less abstract, and let's imagine that my input is 3 and my output is negative 14. That is saying that this function, whatever this machine is, so essentially you drop the number 3 into this function, you crank, there's a handle that you crank, and then out comes the number negative 14. If you have an inverse function, you can reverse this operation, which is you can take a negative 14, you can put it into the inverse function, you can crank the handle, and a 3 is going to come back out again. And that's what this means. That's what it means for a function and its inverse undo each other. Now, the inverse of a function, another way to tell whether or not you're going to get this is, let's say you've got a graph. Usually you can predict this. You've probably done this one enough times. Probably a little bit harder for you to anticipate this one. I don't want you relying on this rule, but it's something to add to your toolkit, which is A good way of predicting whether or not the inverse is going to be a function is if you have a every x value produces, not only does it only produce one y value, which is the requirement for the vertical line test. You can see both of these, the blue and the red, they pass the vertical line test. But another aspect of this is producing a unique y value. So for example, here is the point for x equals -2, -1, 0, 1, 2, and so on. And you can see these are always increasing, going from left to right, which means that the y values are always going to be different. And that means that not only is this a function, but its inverse is going to be a function. Over here, on the other hand, when x is equal to -1, we have a y value of 1. When x is equal to +1, we have a y value of 1. So I have two different x values that give the same y value. This is still a function. This is going to pass the vertical line test, but when this parabola gets tilted over onto its side, so the inverse of this is going to look like that, then obviously we are immediately going to see a failure in the vertical line test, and you can see there is the failure that focuses on those 2 points. There is no such thing as the horizontal line test, but more or less that's what we're saying. This also passes a horizontal line test, which means that the inverse will pass a vertical line test. This one fails a horizontal line test, which means the inverse will fail a vertical line test. You're not going to be relying on this as your method of determining whether or not you have an inverse function, and certainly you won't be relying on this very often to determine whether or to prove you have an inverse. Now, again, as I mentioned before, we're usually interested in algebra. So what about algebraically? Now, when we started off this lesson, I did do a little bit showing you the algebra of this. So I've been asked to find the inverse function of this function. So I'm starting off with a function, and this is a parabola. But I've been asked to find the inverse function, but you need to remember the first thing you're going to do is find the inverse relation. You cannot assume that this is a function. Now, you don't have to write this. I'm writing it here just for clarity. An inverse relation, what do? I start with my function, but I want to put my function into an xy format, meaning I want to introduce a variable. Typical variable we put for the function itself is going to be the typical independent or dependent variable y. Then, and it's important that you denote this, you're going to swap x and y. And so now my new expression, my new relation, becomes this. You need to indicate this. This is in a communication aspect of things, because otherwise, how did you go from here to here? Going straight from here to here leaves a giant question mark on, do you actually understand what it is that you're doing? Here, at least, you're being explicit. You're telling me, I'm changing this around because I'm trying to find the inverse. Even better here, but I'm not going to require you to write this because it's awfully wordy, would be to say, to find the inverse, swap x and y, because technically that's what you're doing. And then once I've done that part, I'm going to rearrange. So I'm going to add 6 to both sides. I'm going to divide both sides by 3. And then I'm going to take the square root of both sides. Now, I'm taking a square root with a variable involved, so I have to remember this plus or minus x plus 6 over 3. So there is my inverse relation. Now, is that a function? We know that we started with a parabola, and there was no domain specified for this parabola, so it's unrestricted if such a thing is possible. It is the widest or the largest possible domain for this one, and we know roughly what this parabola is going to look like because it's shifted down by 6, so there's -6. It opens up and it has been vertically stretched. I've done a terrible job of drawing that. Let's try again. -6. There we go, a little bit better. So it's going to look something like this. When it gets turned over onto its side, it's going to fail the vertical line test. This is a radical relation, and the plus and minus means that it's going to have a top branch and a bottom branch. So in order to find the inverse function, I need to take this and I need to restrict the domain of f, or we can restrict the domain, let's say restrict the domain of f inverse. I can't say that, sorry. Let me just back up there. I have to restrict the domain of f to make the inverse a function. I was about to break a rule there because I was going to refer to f inverse immediately, but we don't have f inverse yet. So I have to restrict the domain of f so that I make this inverse a function. Now, how do I do that? Well, I mentioned previously the idea that failing the vertical line test in the inverse is the same as failing a horizontal line test in the original. So how could I get this thing to pass the horizontal line test? I could do two things. I could eliminate this branch and only have this left-hand branch, or I could eliminate this branch and only have this right-hand branch. And either of those is valid, and doing that is known as restricting. So I'm going to restrict the domain of the original function. So what are my two options? Option one is I could say the domain of f is x member of the reals such that, and what am I going to choose? Well, I'll choose the positive case first. So I'm going to choose this as my first case, and I'll choose this as my second case. So my first case is going to be that x is always greater than or equal to 0. And if I do that, then my range of f, to be honest with you, I'm actually done at this point in time. I don't need to talk about the range of f. All I need to do now is I need to say, what is my inverse function? If the domain of f is these x values greater than 0, then which part of that is going to be, what part is that going to give me for the inverse function? You know what, maybe we do need to go a little bit further here. The range of f at that point in time. So if I choose this right-hand side, the domain is all x values greater than or equal to 0. What's my range going to be? That's going to be y values greater than or equal to -6. The range of f is y member of R, y greater than or equal to -6. Now, if that's the case, how do I find my domain of f inverse, or my range of f inverse? And if you recall the definitions of inverses, it just means you swap the x and the y. So the domain of f inverse is actually going to come directly from the range of f. So it's going to be x member of R, but instead of y greater than or equal to 6, it's going to be x greater than or equal to -6. And here I get y member of R, and I'm going to bring this value down, or this restriction down, y greater than or equal to 0. And if you think this through, this is saying my y value is greater than or equal to 0. So how does that translate to my original expression? Which of these corresponds to a y value greater than or equal to 0? Your first instinct is probably to say the plus. And another way to reason this through is that the result of a square root is going to be positive. And so, yes, it is in fact the plus, because this will be positive, and we want a positive and a positive. So now I can say that f inverse of x is equal to the square root of x, what was it, plus 6 divided by 3. But that is with this understanding that this is my domain and this is my range. Now, you technically don't have to do any of these three. If all it asked for was the original, if all it was asking for was the inverse function based on the original, you just have to restrict the domain of the original, and that everything else follows from that. But in general, you're going to want to do some of these other things so that you can document your thought process in getting there. So here we have f inverse of x is equal to this, and the domain of this says that x must be greater than or equal to negative 6. We need that to be true so that we don't get a negative result in here. And then we say, well, the fact that this range is greater than or equal to 0, we've already taken care of that because we have eliminated the negative in front. I'm not going to take the time to do case 2. I will leave that to you as an exercise. The only difference there would be you would start with this domain, except for you would start with a domain of x less than or equal to 0, and you would proceed from there. And I believe that's it for this lesson. So good luck reviewing inverses, and make sure you get any help on this sooner rather than later, because this is something that we're going to be making a lot of use of throughout the course.